Okay, so welcome back to another video. So here we have a nice little limit. Our objective is to, of course, evaluate this limit of, as it approaches infinity, of n to the power -3/2. Inside we have n plus 1 to the power n plus 1 times n plus 2 to the power n plus 2, all the way up to 2n to the power 2n, and then inside that, close that parentheses off, and then raised to the power 1 divided by n squared. So you'll notice that inside is going to be a product series that we can actually just simplify things down a little bit. And as you notice that in order to take such limit, we want to assume that it's the continuity exists such that we can actually utilize the natural log properties. And you're going to note that as you take the natural log of a product series, you'll see that you can actually use that continuity to change that into a summation of natural logs. With that in mind, and a lot of details going along the way, there's also going to be some integrals involved, which that makes the limit itself a nice problem / question to evaluate. And the answer actually comes down to something very nice and beautiful. So a lot of things, and then all the detailed explanation will go further as we continue on to get to that answer. So with that, why don't we actually just jump right in? So it's worth noting that our series over here, let me just call this L. So if you rewrite this, this is going to be the limit as n approaches infinity, n to the power -3 divided by 2. So this entire thing is a product series. So this can be written as the nth product. So product series, we have that k is equal to 1 of n plus k to the power n plus k, and then close that off. And then of course we have 1 divided by n squared as that exponent. So assuming the continuity exists, so let's actually take the natural log of both sides. So I would have the natural log of capital L, and then set that equal to the limit as n approaches infinity. So then that would mean this will bring that down to the front of the n, and then change that as the natural log of all that. And if you're actually taking the natural log of this entire thing, so that means we're going to have a sum of natural logs. So we have, of course, -3 divided by 2 to the power, or multiplied by the natural log of n, and then add this. So of course, I can actually bring down the 1 over n squared to the front of that as well. So 1 divided by n squared of the natural log of our product series over here. So k is equal to 1 all the way up to n, then n plus k to the power n plus k, and then we can close that off. So as I mentioned, we can of course take with the continuity, as we take the natural log of product series, we can actually change that and switch it up so that this becomes a summation of natural logs. So applying that logic to that, so now what we have now is going to be, and also well, we're also going to bring the 1 over n squared to the front of our summation series as well. So it's not as dependent because it's only dependent on k, not n, and it's going to be the number. So this will yield us with the limit as n approaches infinity of -3 divided by 2 natural log of n. Then now we have our partial sum. So this is going to be all the way up to n, and then k is equal to 1 of n plus k multiplied by the natural log of n plus k, all this being divided by n squared. Okay, and then here's something to note, because now the next step is of course to evaluate. As you can see, we need to figure out what the our partial series is going to equal to. So we're actually going to have to do a little bit of a manipulation in algebra. So we want to note that over here, this function over here, our natural log of n plus k, we're going to change things up a bit. This can be written as the same thing as the natural log of n multiplied by 1 plus k divided by n. Now the next thing is, of course, we're actually going to take into our focus of this partial sum over here. So let me actually write the asterisk such that we're actually calculating our partial sum. So n, then k is equal to 1 of n plus k divided by, or multiplied by n plus k, and n divided by n squared. Simply, of course, same thing written as our partial sum. K is equal to 1 of n plus k, then multiply by, so we applied the natural log properties, natural log n, then plus the natural log of 1 plus k divided by n, then all this still, of course, being divided by n squared. Then we can continue forward and then break this up as a sum, as an addition of sums. So then now the following we would attain our partial sum, and k is equal to 1 of n plus k inclusive, or in the parentheses, multiplied by the natural log of n, then this being divided by n squared. Add this with our partial sum yet again, so k is equal to 1 to n of n plus k multiplied by the natural log of 1 plus k divided by n, all this being divided by n squared. And then it's worth noting over here that because we have ln of n and n squared does not depend on our variable k, I can actually factor those terms outside. So I have the natural log of n divided by n, and then multiply by our partial sum, n is equal to k is equal to 1 to n of n plus k. And then you'll notice that n and then the plus k here, first off, for our term of just k specifically, we can break this up in terms of sum. You'll notice that if I take the partial sum of just k, that's basically just taking the sum of natural numbers. So it's already have its closed formula. And then n, which is not dependent on this, that means it's just taking n, adding n many times, so that's n squared. And then you would apply the algebra and get that this is just going to be the natural log of n divided by n squared multiply by 3n squared, and then plus n divided by 2. So that will be what this is equal to. So next thing we need to do is we need to figure out what this one is. Okay, so now next is our partial sum over here. What I can do here is, let me actually divide an n to both the numerator and the denominator. And with that, we can actually just factor that outside of our partial sum. So then that'll just lead us with just 1 divided by n, then multiply with our partial sum, k is equal to 1, multiplied by 1 plus k divided by n, multiplied by the natural log of 1 plus k divided by n. So I'll actually draw this brace over here just that it's actually associated with this term, and so this term is associated with that term. Okay, so we have all that together, so now we can actually simply just put the pieces together and note that we have, so far, we have achieved the following. I'm just going to write this, the asterisk, just to continue where we left off. So now we can actually just substitute things back in together. So now, so far, I would have that this is going to be 3 times the natural log of n and then divided by 2. So I'll just write like this, 3 over 2 times ln of n. And then add this with the natural log of, so I'll just cancel out one of the n. So yes, so natural log of n, then divided by 2n. And then we have this sum. But here's something you want to note, that this is very interesting over here. If you actually pay attention to the way things are set up in the partitioning sense and all that, this is actually satisfies the definition of a definite integral. So you'll notice that if you actually take for, if you actually play around with the pieces specifically, if you take your bounds carefully and then put in whatever function you're actually like taking the partitions of, then the subintervals in that case is what I meant to explain. So you can actually utilize the definite integral definition and get that this is the same thing written as the definite integral from 0 to 1 of 1 plus x multiplied by the natural log of 1 plus x and then dx. So then I'll just put this back over here. So now this is what we have now. 0, 1, and then what is it? 1 plus x multiplied by the natural log of 1 plus x and then dx. Okay, so now just to put everything back together, so what we have so far. So now I have that, so far we have that the natural log of L is going to equal to, so let's see, still the limit as n approaches infinity. So -3 divided by 2 natural log of n. Add this with 3 divided by 2 times the natural log of n. And so of course, add this with the natural log of n divided by 2n. So I'll close that off. And then now we have that plus the integral from 0 to 1 of 1 plus x multiplied by the natural log of 1 plus x and then dx. So you'll notice that, of course, we have some terms that cancel out. We have that these two, the 3 over 2 ln is going to cancel out. And so we just have this term and we still have this integral to calculate. But the calculation of the integral itself is pretty self-explanatory. You'll notice that I can actually just do a nice little u sub. So to perform this, I'm going to let me actually write this on the side. So the integral from 0 to 1, 1 plus x, natural log of 1 plus x, then dx. We'll let u equals 1 plus x, then of course du is going to equal dx. Then now what we have now is, of course, we're going to have to change our bounds. So 1 plus 0 is going to be, what is it? So then we have 0 plus 1, that's going to be 1 on the bottom, and then this is going to be 2 over here, going to be u, and then ln of u du. So we're gonna have to do a little integration by parts. We're gonna let v equals the ln of u, then dv is gonna be 1 divided by u du. Then we let, I'm just gonna call this dw. So dw is equal u divided by u times du, and then w is gonna be 1/2 multiplied by u squared. So you put everything back together, so v times w, so then that's just yield us with 1/2 u squared, and then times ln of u, evaluate this from 1 to 2, and then subtract, so multiply this together, so that means I'm gonna have 1 to 2 of u divided by 2 du. And so perform the necessary calculations together, we're gonna have that this is gonna be 2 times the natural log of 2, then subtract 3 divided by 4. Okay, so that's gonna be, that simplifies things a whole lot better. So now continuing forward, that we have so far the limit as n approaches infinity. So to reinstate things again, natural log of L is going to equal limit n approaches infinity of the natural log of n divided by 2n. And then add this with 2 times natural log of 2, 2 times natural log of 2, and then subtract 3 divided by 4. And then you're gonna notice that the only thing we have to take the limit of is this function over here, which of course, if you take this as it approaches infinity, you're gonna get a indeterminate form of infinity over infinity. You can apply L'Hopital's rule, say that you can actually take the derivative of both the numerator and denominator. Ln of n is going to be 1 over n, and then 2n is simply just going to be 2. Take that limit again, so you're just going to have that this is going to equal 0, and I just abbreviate L'Hopital LH for applying this rule. So now to continue with that, so all we're left with, and that's already the only function we already take the limit of, so that means we're pretty much done. So natural log of L is then going to be 2 times the natural log of 2 minus 3 over 4. And then, I don't know why I wrote that parentheses over there. Okay, and then now the last thing is just take the e base of both sides, so we're just left with L, which is what this whole thing we have to calculate. L is then equal to e to the ln of 4, because I just moved the 2 back in, so ln of 4, and then minus 3 divided by 4, which therefore is going to be the same thing written as 4 times e to the power negative 3 divided by 4, which of course that is our final answer to this long limit of inside of our products, and everything just comes down simply. A lot of whole work, a lot of manipulation specifically with everything we're doing with the partial sums over here, which I know looks like a lot, but it starts to come together when you actually break down the finer details little by little. So with that, there you have it. And yeah, that's pretty cool if you ask me.